sac114 problem number 7. Find the acceleration of a block sliding down a flat surface at angle theta to the horizontal if the coefficient of friction between the block and the surface is mu sub k. Okay, let's make a sketch of that first. Make that our flat surface at angle, there's our horizontal, so at angle theta to the horizontal. Put a block on there. So it's sliding down the ramp. If it's sliding down the ramp, there'll be a frictional force in the upward direction. Let's go ahead and draw a free body diagram for this object. We'll go, I do want to indicate the angle in there is necessary, and then draw all the forces acting on the object. We've got the weight of the object acting straight down toward the center of the earth. Call that mg. The block itself is sliding down the ramp. So, by the way, there's going to be an acceleration in the up the ramp direction. Let's put that on our free body diagram too. Nice arrowhead there, eh? Alright, but we got an acceleration in the up the ramp direction. What else have we got acting on this? There'll be the frictional force in the up the ramp direction. Call it lowercase f, which we know is just mu sub k times n. And n, by the way, is acting in a direction perpendicular to the ramp. And of course we've got our angle theta in this picture as well. Alright, for applying Newton's laws, we're in a little bit of a pickle here because we got force and acceleration up the ramp direction, one perpendicular, but then we got this rogue force, I'll call it, the weight, which is acting in neither the up the ramp direction nor the perpendicular to the ramp direction. So I am going to call the down the ramp direction the x direction. Let's go ahead and label that on there. We'll call this the x direction, and the perpendicular to the ramp direction the y direction. And that'll be the coordinate system I'm going to work in. So I got to break this vector up into components along the x and y coordinate directions. Let's go ahead and draw a little vector component diagram for that vector then. So I'll call that the x direction. Nope. I'm going to use a coordinate system, the one that I stipulated up there in yellow, and indeed I'll draw it in yellow. So the perpendicular to the ramp direction is the y direction, and the along the ramp direction as the x direction. And then the weight vector that I'm trying to break up into components is in the straight down direction, which can be thought of as having a component in both the x direction and a component in the y direction. So I should say a component in the x direction, a component in the y direction. Of course, they have right angles to each other. So this is w. This will be wx and wy. I'll put the magnitude here. Wy itself clearly going to be negative because it's in the negative y direction. But we are, I think I'll take those absolute value signs off. So this is the magnitude of the vector. Here's the direction of the vector. And we've got to get this angle theta into this picture over here. So I want to draw, go and extend the x-axis just a little bit. Draw horizontal over here. So here's my theta, taking it directly from this picture up here. It's the angle between the surface of the ramp, which is my x-axis, and the horizontal. And then looking at this big triangle here, that makes this 90 degrees minus theta, So this angle in here, looking at the small right triangle that I just made, this angle and this angle have to add up to 90, so this has got to be theta. So with the way I chose to draw this vector component diagram, I get this is the angle theta, so Wx over W is the opposite over the hypotenuse. That's the sine of theta. Wx is W sine of theta. If one just memorizes that the x component usually turns out to be the total vector times the cosine of theta and uses that without drawing a picture and working it out for the case at hand, one can get into a situation where the answer is simply wrong. They're doing the wrong thing. But this case, with that being chosen as my angle theta, with this diagram, Wx is W sine of theta, and then similarly Wy over W is equal to the cosine of theta. So Wy is W cosine of theta, where W itself is mg, so I'll call that mg sine of theta for Wx, and mg cosine of theta for Wy. These are my two intermediate results. Now I'll go ahead and put these two vectors, one perpendicular to the ramp in this direction and one along the ramp, on a new free body diagram that I draw to replace this one. So I don't want to put components and the original vector on the same free body diagram, but I'll draw a new free body diagram with this vector replaced by its components. So I'll have the object, the normal force, the frictional force, which is mu k times n. I'll put the acceleration as an arrow that's not touching the object but is near it. In the up the ramp direction, call that A. And then we had our Wy component, which was mg, left out the g there, cosine of theta, and the x component, this one up here, Wx, which proved to be mg sine of theta. Okay, now I'm ready to sum some forces, set it equal to the acceleration. I'm tempted to sum the forces in this direction directly, but I'll get that frictional force in there, which has an n, so at some point I'm going to need to know what n is. So I choose to sum the forces in what I call the y direction. It's in the direction up and to the right perpendicular to the ramp, and that's going to be equal to the mass times the acceleration in that same direction, which is just 0 by inspection, so I'll just write it as 0. So I got n, some summing forces along this direction, calling that away, the direction which n is the positive direction. Wy is in the exact opposite direction. So that goes into the summation with a minus sign. And I'll write it out as I have it indicated on the diagram, mg cosine of theta. And that's equal to 0. So the normal force is mg times the cosine of theta. I have an expression for the normal force in terms of given quantities and perhaps m. Let's see if m was given. Yeah, m is not given, so I've got it in terms of some given quantities plus m. Only theta and mu sub k are given. So theta is known, g, universal constant, but m is actually not known. However, that's not going to stop me from proceeding. I'll sum the forces in the up the ramp direction. Sum of the forces in the up the ramp direction is going to be equal to the mass times the acceleration in the up the ramp direction. I am, of course, looking at this free body diagram, and in fact, I'm going to start that over here. Erase that first so it doesn't get in our way. Clutter things up later on. So I can see this diagram, sum of the forces, and the up and to the left direction is equal to the mass times the acceleration in that same direction. Okay. The frictional force F is in that direction, Wx is in the exact opposite direction, and we do have some acceleration in the direction that I just talked about. I called it A in the diagram. Replace an F with what it is, mu sub k times n, minus a W, replace with what it is, mg sine of theta. I get all this stuff is equal to the mass times the acceleration. Okay, and n we've found to be mg cosine of theta, so I can write mu sub k mg cosine of theta, just replace n with what it is. What we found it to be, mg sine of theta, being subtracted from that, is ma. And here, lo and behold, the masses do cancel out. Divide both sides by m, use the fact that m over m is 1, and effectively canceling all those out. So I get, as a final result for A, which I think is what we were solving for, mu k g cosine of theta minus g sine of theta. Before I frame that, I want to make sure that's really what I was asked to find. Find the acceleration of the block, where the block is sliding down a flat surface. Okay, so that's the magnitude of it, and the direction is in the up the ramp direction. Let's go ahead and write that in the up the ramp direction, which the up the ramp direction is, of course, the direction along, parallel to the surface of the ramp, which brings it down, narrows it down to either that way or that way, and the up the ramp direction is that way, the way that we've indicated in the diagram. So acceleration is a vector. We should give magnitude and direction, and we've given both.